Do you remember at the beginning of this chapter, I said you can use identities to help make things a lot easier when you're solving? Yeah, because check this out. Some trig identities actually have more than one trig function in them, like this question right here. Oh my gotcha, what do I do? Okay, don't worry about it. To solve these types of trig equations, all we have to do is use the identities. Oh, okay. Well, let's go to town. Let's see what I can do here. I just happen to have the identities ready and available. Ah, look at that. Okay. So let's take a look at question example 1A here. Check this out. I can't do anything with this. Yes, you can. Recognize that this is sine 2x. Soon as you see that sine 2x, there it is. It's a double angle identity right down there. So rewrite it. This becomes 2 sine x cos x. This guy doesn't change at all because it's in its most simplest form, right? This all equals to 0. Look what you can do. This is going to freak you out. You got a cos x as a common factor to both of those. You also have a 2 that's a common factor to both of those. So guess what? GCF. Take out a 2 cos x, and look what you're left with. That's leaving you with sine x minus 1. Can you solve that? Of course you can. You've done 1,000 of these already like that. So let's go out and do it. Check this out. This becomes 2 cos x equals to 0. This becomes sine x minus 1 equals to 0. And you know how to solve ones like this. Isolate first, divide by 2, divide by 2. This gives you cos x equals to 0. Bring the 1 over. This is sine x equals to 1. And now, again, if it wasn't a quadrantial point, I would say, okay, then go out, use the cast rule, absolute values, solve, and all that other stuff. But the nice thing about this one here, sports fans, is those are quadrantals. Think about it. Where is cos 0? Cos is 0 here, cos is 0 there, isn't it? Of course it is. So it's at, well, is this in radians or is this in degrees? Does it show? Aha, look at that. It's in radians. Okay, so for 2 pi, let's figure it out. There's radians at pi over 2, and there's radians at 3 pi over 2. There's your solution so far. Pi over 2 and 3 pi over 2. Now let's do this one. Where is sine x equal to 1? Oh, equal to 1, there's only one spot, right there, at pi over 2. Okay, so this means, do we have to write the pi over 2 again? Heavens no. There's your answer. Look how pretty that turned out. Oh my goodness, this is just so beautiful now that you have a few identities. It makes equations so much easier. Okay. So let's go over to this one. Look at this monster. Well, it's not a monster. It's nowhere even close to being a monster because think about it. You got to be smart here. You got to be smart here. One of the things you have to see is you have to see where this is going. Okay, so first things first. Notice that this is cos 2x. It's one of the double angle identities. And like I said in previous podcasts, always use this top one. That tends to be the easiest one to play with because that makes it a nice Pythagorean identity. Yuppie skeppy. Okay? So watch this. This is 4 minus 7 sine x equals 2. Oh, look at that. That is just cos squared x minus sine squared x. That's the identity right here. Okay, perfect. Now, with that, since I don't have any more identities to play with, well, actually I do. I have one more. Notice how this is in terms of sine, this is in terms of sine, but this is in terms of cosine. Oh, dagnabbit. One more time, let's use the Pythagorean identity here. And realize that cos x, or cos squared x, equals to 1 minus sine squared x. Oh, beautiful. So let's just take this guy right now and substitute it in. Okay, easy peasy. That leaves this as still 4 minus 7 sine x. This now becomes 1 minus sine squared x, right? Minus sine squared x. Oh, how beautiful. Now I've done everything I can with the identities. Let's put that identity sheet away. It's just in the way anyways. Now, let's clean it up. Okay, notice this is still 4 minus 7 sine x. Can't do anything there. I've got a 1 here. Oh, look at this. Combine like terms. I have minus 2 sine squared x. This is basic algebra, isn't it? Take all of this, bring it over to the other side. I'm not proving an identity here. I am solving, so I don't have to keep left-hand side, right-hand side separate. I can bring it over. I'm actually trying to solve this, and that's what algebra is all about, combining like terms. So what do I have? I have a 2 sine squared x minus 7 sine x. Make that look like a 7. There it is. Okay. I have a 4. I'm bringing that 1 over, so now I have a plus 3. That equals to 0. Does that look familiar to you? I think it looks familiar because guess what? Put an A here. Put an A here. Look what you have. You have 2a squared minus 7a plus 3, don't you? Equals to 0. I see a trig, well, not only a trig function, but a trinomial that I can factor. Yep, there it is. PSA 2, you betcha. Okay, front and back, 2 times 3, that's 6, that's minus 7. Two numbers to give me 6 that add up to minus 7. Oh, easy. Minus 6 times minus 1, because minus 6 plus minus 1 gives me 7. Now I can write this guy out. Here we go. 2a squared minus 6a minus a plus 3, the decomposition method. If you want to go look it up. Yep. Take out a 2a here, leaving me with an a minus 3. Take out a minus 1 here, leaving me with an a minus 3. Beautiful. This is 2a minus 1. This is a minus 3. And check out what I can do with this now. This is the best part. Let it equal to 0. There's your 2a minus 1 equals to 0. There's your a minus 3 equals to 0. Now I can solve. A equals to 1/2 and a equals to 3. Now, do you remember what a was? I don't know. I got to go back. Where's a? What was? Oh, it was sine. Oh, check this out. Sine of x then equals to 1/2. This is sine of x equals to 3. That's weird. That's weird. Can sine x actually ever equal to a number that big? Check it out. You don't believe me? Watch what you can do. Go to your calculator and see if you can figure it out. You know, and I know to do this, you have to take the inverse sine of both sides, right? Inverse sine, inverse sine. Watch what happens if you try to take the inverse sine of 3. This is going to freak you out. Ready? Second inverse sine of 3. Watch this. Boom. Error. Error. The value entered is not allowed in the function. Why? Oh, I know what you're saying. Oh, it's because we're in radians. We have to convert it back. Okay, so let's convert this. Let's flip this over to my mode. I'm going to flip it over to degrees, and away we go. That should work now, right? Okay, so I'm going to go second inverse sine of 3, and look, oh, I get the same problem. Think about it. Sine can never be bigger than 1. Look at your unit circle. Your unit circle is, guess what? The biggest number for sine is 1. You got it equaling to 3. Can't do it. Cool. So guess what you got to do now? Yes, you still have to do that procedure, that 4 procedure. You isolate it first, right? You isolate first. That's the first thing you did. Well, we did that. The second thing, yes, you got to use your cast rule. So if you use your cast rule, add sugar to coffee. Yeah, you still got to go through that whole procedure there and there. Okay, there's your 2 angles. Now we take the absolute value of this, which is really pretty. We've already done that. And now remember, where is sine equaling to 1/2? Well, it's right here, right? That's at that point, which we refer to as pi over 6. Okay, so that theta or x, right, reference angle is pi over 6. So that means this is pi over 6. That means this reference angle is pi over 6. Now, figure it out. Figure out where you are. Yep, you're at pi over 6 and at, oh ho! Remember, this is 6 pi over 6 way over here. That means this is 5 pi over 6. So your answer then is pi over 6. Well, we got that already. And 5 pi over 6. You just solved it. Oh my goodness, impressive.